In this video, I want to go over an example of a fuzzy control system. The example is using fuzzy control to enable a mobile robot to track a path on the floor, where the path can be a straight or curved path. The tracked path is captured using a camera. So these slides are taken from a presentation that I gave in 2014 in a local conference. So the title of the presentation is Vision-Based Autonomous Path Tracking of a Mobile Robot Using Fuzzy Logic. So all the materials related to this example are posted on Moodle. These include the MATLAB codes, the full paper, the presentation, and the demonstration video. This will also be our last lecture for this course, as we have now approached the last week of the semester. The outline of this presentation is as follows. So we will go over introduction, modeling of the mobile robot. We will look at the proposed method and the control scheme to control the mobile robot. We will look at experimental results, and we will look at the conclusion. So let's move on. Path tracking is one of the problems in the field of mobile robot navigation. So this is where the mobile robot navigates in its environment by following a visual path on the floor. So the path can be a straight or a curved path, and such robots have applications in manufacturing facilities, for instance, whereby the mobile robot delivers parts from one location to the another. It can also have applications in package fulfillment centers, whereby the mobile robot delivers packages from one location to the other. So the problem here is to design a control system for a mobile robot to track or to follow paths of different cabbages. So one of the ways in which this problem can be solved, or one of the approaches, is by using fuzzy logic or knowledge of fuzzy logic. And since fuzzy logic captures human expert knowledge in fuzzy rules, which are in the form if, then, else, then we can apply the knowledge of a human expert driver, that is the knowledge of driving cars, to control the speed and the steering of a mobile robot. So the advantages of such an approach is that it is an unconventional method. So we have seen that fuzzy logic based method for a controller or a fuzzy controller is an unconventional method. So in this case, no dynamic model of the mobile robot is required, and it can emulate human driving behavior. So inputs of this system are through a vision sensor or a camera. So a camera is able to capture an unknown path that is traced on the floor, and it can provide that information or information about the path to the control system. So this area of research is similar to the research in self-driving cars, whereby a camera is used to detect, for example, vehicle lanes and detect signs on the road, and then use that information to control the car. Next, let's look at the model of the mobile robot for which we are trying to design a fuzzy control system. So the model is a differential drive mobile robot. So if you look at the figure here, this shows a top view of the mobile robot. So it's a differential drive mobile robot, which means that it has two active wheels which are powered by motors, which are here. This is wheel 1 and this is wheel 2. And basically they're independently controlled by two different motors. So by varying the velocities of the two wheels, you can control the trajectory of the robot. So in other words, you can control the steering of this robot or the steering angle and the forward velocity of this type of robot by varying the speeds or the individual speeds of the two active wheels. If you look at the dynamics of this robot, it is given by equation 1 here. So let's say this is a coordinate system, XY coordinate system, whereby X is the X position of the robot. So the position is in reference to the center of the two wheels at this point here. And an angle is the angle theta given here, which is the position or the angle of the mobile robot with respect to the positive x-axis. So x dot is given by v cos theta, where v is the forward linear velocity of the mobile robot. Y dot is given by v sine theta, and theta dot is given by omega. So omega is which is this, the rate at which the mobile robot tends along an axis. So this axis depends on the individual speeds of the two wheels that are here. So this the kinematics of this robot is highly non-linear, so it cannot be controlled by a linear control system. In addition, it has a non-holonomic constraint, which is given by x dot sine theta minus y dot cos theta is equal to 0, which basically means that the mobile robot is unable to travel along the active wheel axis, which is this axis. So it cannot travel in this direction. So there is no way in which it can travel in this. So this is one of the constraints. It cannot travel along this axis. It can only travel along the this axis. So moving on. So one of the ways in which we can control the position and the angle of this mobile robot is by controlling the steering angle and the forward velocity of the robot. So forward velocity is given by v, and the steering angle is this angle here. So the mobile robot has 3 wheels. So as I've said, 2 are active wheels and the third wheel is a passive wheel, which will tend in the direction in which the robot is turning. For example, if the robot is turning this way, then this wheel is going to turn in this direction, in the opposite direction. So this is a free wheel. So it is not powered, and it can basically move in the direction in which the mobile robot is steering. So this steering angle is given by this here. So the mobile robot angular velocity omega is given by v over L, where L is the distance between the wheel axis and the wheel which steers, or the free wheel, the axis of the free wheel. And so v over L times tangent of this variable phi, var phi. And steering angle has the limit minus pi over 2 to pi over 2. That means the maximum steering can be when the wheel, which is a 90-degree angle, like this angle, for example, up to this. So it can, if the steering angle is, let's say, 90 degrees, then basically the mobile robot is going to turn along one of the wheels. And it can be also in the other direction as well. So positive and negative 90 degrees. So that's the limit of the steering angle. So we can command the steering angle, and we can command the forward velocity. And so those can be translated into individual wheel speeds, and we can apply those individual wheel speeds and achieve those forward velocity, linear velocity, and the steering angle that we desire. And then the position and the theta of this robot is going to change accordingly. Now on the vision dynamics. So basically vision dynamics is referring to how we can capture the unknown path that is traced on the ground. So in this case, as mentioned before, we are going to use a camera to capture the path. So let's say this is the path that is on the ground. And let's say this is the top view of the mobile robot that is trying to track this particular path. So over here, C is the curvature of the path. And basically 1 over C is this radius along an axis for this particular curvature. So in this case, we have two types of errors that we want to provide to the control system. One is E sub L, which is lateral error, which is this error. So we don't want this error. So this error is taken from a distance of L from the center axis of the wheels. So this is the lateral error. And then another error is the heading error. Heading error is basically this angle that this particular curve makes with the horizontal axis. So there are two types of errors. One is heading error and the other one is lateral error. And basically, as I've said before, curvature is C, and so this distance, this like radius is 1 over C. So moving on. So the proposed control scheme is given using this block diagram. So we have a vision system which provides these two errors, which is the lateral error and the heading error. And the vision system also provides a curvature input. So it gives the lateral error and the heading error. And using that, we have two fuzzy controllers. One is a fuzzy steering controller. So this is going to control the steering of the mobile robot. So this controller is going to take the lateral and the heading error and give us desired steering angle. And we have the second controller, which is fuzzy velocity controller. So the fuzzy steering controller is simple. It's controlling the steering of the mobile robot. So the second controller here, fuzzy velocity controller, what it does is it takes two inputs, curvature and the steering from the fuzzy steering controller to control the forward velocity of the mobile robot. So the forward velocity, why it controls the forward velocity? So that the mobile robot is able to track the path accurately. So for example, when the mobile robot is following a curvature, what we want is, we don't want it to follow a curvature like this using a constant velocity, okay? Because it might become unstable and then maybe move out of its path. So whenever our system detects a curvature, we want to command a velocity that is able to track this path, this curved portion safely. And then when we go to a straight path, we can command the maximum velocity. So for tracking straight paths, we can have maximum velocity whereby there is no curvature. But when it's coming or approaching a curved section, we want to reduce the forward velocity so that it safely tracks the curved path. So this is similar to a human expert driver. So for example, this is the way we drive. On straight roads, we drive very fast. But when we come to curves or bends in the road, what we do is we slow down. And the reason we slow down is so that we are able to steer properly and to steer through this bend properly. So that is the idea that we want to, that is the human knowledge or human expert knowledge that we want to emulate in this mobile robot. Now, then there is a low level controller. So the low level controller has a steering angle and the forward velocity, and it commands the mobile robot wheels. So this commands the wheels of the mobile robot, the two independent wheels, velocities. So this low level controller can be implemented using any method like a PI control. And then it commands the speed of the velocity of the individual wheels. And then it is going to follow the path. And then we take the actual part information as a feedback. So this is a feedback using a camera. So we take a feedback using a camera and then we feed it to the vision system to do the computations and provide these errors and the curvature to the two fuzzy controllers. And they will again control the steering and the forward velocity to control the mobile robot. So this is the proposed control scheme that is used in this research. Now moving on, some more details about fuzzy steering controller. So we have two controllers. So this is the first one, steering controller. So this provides the steering angle of the mobile robot to track a path. So this is like a tracking controller which tracks the path. So it has two inputs, lateral and heading error is combined to obtain the tracking error. So we find the tracking error using this equation. We combine the lateral and the heading error. So basically the tracking error E sub t is equal to alpha times EL of k plus 1 minus alpha times EH of k. So alpha is the parameter that controls the two errors. So if alpha is 0, then we basically don't consider the lateral error. We only consider the heading error. And if alpha is 1, then we don't consider the heading error, only consider the lateral error. So alpha is between 0 and 1. So this is between 0, 1, and it proportionally controls or divides the total error into lateral and heading error. So the two inputs are represented by the linguistic variables error. So one of the linguistic variables is error, which is E1, and the other linguistic variable is change of error in the fuzzy system. So these are the inputs of the fuzzy system. One is error, which is E sub 1, and the other one is change of error, which is E sub 2. So E sub 1 is basically this tracking error, and E sub 2 is the change of error, which is the current error minus error. So this is the current tracking error, since E1 is E of t minus the tracking error at previous sample. So E1 of k minus E1 of k minus 1. So error and change of error. So over here we know k in discrete control is the sample number. Okay. Now moving on, more details about the input fuzzy sets. So we have two sets for the range of values for error and change of error. And these two sets are negative, which is capital N, which is here, and positive. So we can say that the error or the change of error can be negative or positive. And the membership functions are given here. So the membership functions are linear in this range minus m to m. So the error and the change of error can be either negative or positive. Membership can be easily computed because it's a linear membership function, and basically it varies linearly between minus m to m, where m is a design parameter which can also be optimized. So here we choose m as 1. So between -1 and 1, the membership in positive or negative can be between this value 0 and 1. So if it is totally -m, membership in positive is 0. If it is totally in around this value m, membership in negative is 0, and membership in positive is 1. And if it is 0, then membership in positive is half, and membership in negative is half. So these are the membership functions for error and change in error. Moving on. So the fuzzy rules for the steering controller. So the fuzzy rules are in this form. If error 1 is some value I1 and error 2 is some value I2, then the output U is this polynomial equation, which is a polynomial of E1 and E2 in terms of E1 and E2. And over here, I sub 0, I sub 1, and I sub 2 are the parameters. So this is what we call a TS or Takagi-Sugeno type fuzzy system, where we have rule in this form. So I sub 1 and I sub 2 can be either negative or positive. So E1 can be either negative or positive, and E2 can be either negative and positive. So basically, you have two inputs, and each of the two inputs have two linguistic variables. So in total, we have 4 rules. Okay, so it says I is equal to 1 to n, where sub I, so rule sub I is this. So we have a total of n rules, where n is 4. Because you have two inputs, and each of those two inputs have two linguistic variables. So the consequent part, which is the then part of the fuzzy rules, are simplified as this equation. U1 is equal to P1. So this is the output U1 is equal to P1 times I1 times E1 of k plus I2 times E2 of k. So these are all the parameters: I1, I2, P1, P2, P3, P4. So these are all the parameters of the rules. So over here, it is assumed that I0 of one is, I0 of each rule is 0. So we disregard this bias parameter. So the rules are simplified in this form. So we have only 4 rules for the output. So we have only 4 outputs because there are only 4 rules. Next, so we have 6 parameters in total, as I have mentioned before, which are P1, P2, P3, P4, and I1 and I2. So more details about the inference. So algebraic product is used for fuzzy AND operation and to compute the firing strength or the activation degree. So this is also called activation degree for each rule. Okay. So this is given by capital phi sub I as mu of I1i. So mu refers to the membership of an input in the set AI times E1, and mu of I2 sub I times E2. So basically this is like a product operation. So we multiply both the memberships together, as you have seen for, so this is like a product operation. Okay. Well, this is the product operation. So membership in II of E1 times membership in I2 of E2. So the membership degree. So that's for each rule. So based on this, the values for E1 and E2, we will compute the membership. So that's in the fuzzification process. So in the product operation, to compute the activation degree for each rule, we just multiply the membership degrees corresponding to each rule. So this is considering the antecedent of each rule, which is the if part. And then the defuzzification is using the weighted average method, which is given by this equation, which is the sum for all rules, phi I times ui of each of the rules, and then sum of divided by the sum of these activation degrees for all the rules. So the output is a steering angle, which is variable phi, which is this. So for each discrete sample, we will compute the steering angle for the mobile robot. Next, the parameters P1 to P4, sorry, P1 and P4 are 1, and the parameters P2 and P3 are 0. So this is again done to obtain simplest control rules possible. Now all these parameters P1 up to P4 can also be tuned or optimized using various optimization techniques. So once we simplify the rules, the table of rules are given in this way. So basically U1 is I1 times E1 plus I2 times E2, U2 is 0, U3 is 0, and U4 is I1 times E1 and I2 times E2. So basically E1 can be positive, E2 can be positive, so that's rule. The first rule, when error is positive and change of error is also positive. Second rule is when error is negative, error is positive and change of error is negative. Third rule is error is negative and change of error is positive. Fourth rule is both are negative, error and change of error. So these are the outputs of the rules. Then U1 will be such. And we have seen how to do defuzzification and use this U1 to compute the crisp or the numerical steering angle that we want. Now the control surface for that particular fuzzy rule base is non-linear. So you can see the control surface here. So for all possible values of E1 and E2 between -1 and 1, so we can see the output steering angle, which is here, which forms a surface like this. So this is a non-linear control surface. And this is obtained by choosing the parameters I1 and I2. So the parameters I1 and I2 were chosen in this way. So I1 was 9 and I2 was -0.02, and these were chosen experimentally by running several times and then determining the optimal value of these two parameters. So optimal parameters can be obtained also by tuning. So this was manually tuned. So we can also tune it using various techniques such as a PSO. Now moving on. Now the velocity controller. So this is the second controller. This is the second fuzzy controller, number 2. So it controls the forward linear velocity for safe path tracking. So in the case when so basically the idea is to emulate human driving behavior where we as humans, we drive fast when we see a straight road, we speed up, but then when we see a bend, we apply the brakes and we slow down. So that behavior is emulated using this controller, fuzzy velocity controller. So it says 2 inputs to the fuzzy velocity controller, and these are given by linguistic variables. Steering. So steering is basically given by delta variable phi, which is absolute of phi minus phi max, which is the maximum steering angle. And this is basically delta phi, which is change in steering. So phi max is given by this equation, where we have a maximum angular velocity of the robot, and it's related to maximum steering angle using this equation. So one of the inputs is steering. So steering can have 3 linguistic variables or 3 linguistic values called gentle, appropriate, and aggressive. Okay. So steering angle, if it is within this range, okay, between if it is close to 0, so basically this is change in delta variable phi. So this is change in steering angle. If this is 0, so this is like an appropriate steering. Okay. If it is positive towards the positive, then it is aggressive steering. Okay. And if it is towards the negative, then it is gentle steering. Okay. So that's the change in steering angle, which is given by this equation. So next is the second input is known as bend. So bend is basically the amount of bend in the path ahead. Okay. So this is the amount of bend or the amount of curvature in the path ahead, which is given as the normalized curvature, which is the absolute of the curvature divided by C max, which is the maximum curvature. And this is given by C bar, which is bend. Now C max is given as omega max over V. So this is the maximum curvature that can be tracked by this particular robot. So the maximum angular velocity of the robot divided by the velocity of, or the current forward linear velocity of the mobile robot. So this will change based on the maximum angular velocity and the forward velocity of the robot. And then this is given by, this is the normalized curvature. So the normalized curvature is between 0 and 1. So it has 3 linguistic values as well: wide, medium, and narrow. So if bend is approaching 1, then it is a narrow bend, or C bar. If it is between, if it is approaching 0.5, it's a medium bend. And if it is close to 0, it is a wide band. So these are membership functions that describe the membership in all the 3 sets. Okay. So between 0 and 0.5, you can see that narrow will be, you will have membership 0, but you will have some membership in wide and medium. Okay, and the output of the fuzzy system is for the velocity controller is the velocity scaling factor, or V sub SF. So basically this is going to apply, can be between 0 and 1, which will apply scaling to the forward linear velocity of the mobile robot, which will automatically scale down the velocity of the robot if it is driving through a very narrow band. So there are three singletons used as outputs of the velocity controller. So the linguistic variables representing are low, medium, and high. So the output V scaling factor is low, medium, or high. And the fuzzy rule base is given as this. So you have two inputs. So each of the inputs has three linguistic values. So curvature has wide, medium, and narrow, and steering can be gentle, appropriate, or aggressive. So you have a total of 9 rules, and the rules are given in this way. So if the band is wide and steering is gentle, then velocity scaling factor can be high. Okay. But if there is a narrow band and you have very aggressive steering, then we just lower the scaling factor to lower the velocity of the mobile robot. So based on human knowledge, this rule base has been obtained. So basically the idea is if you have a wide band and the steering applied is gentle, then the velocity can be high. Okay. And if let's say you have a wide band and you have aggressive steering, then you reduce the velocity a bit, medium. If you have appropriate steering and medium band, then again medium scaling factor. You have narrow band and you have gentle steering, then again medium. But when you have appropriate and aggressive steering for a narrow band, then you lower the velocity. Okay, so this is based on human driving experience. Okay. So moving on. Right, so the experimental results. So these are the details of the mobile robot platform. So you can see an image, a photo of the mobile robot platform and the path. So this is the path. So it is a white path on a black floor, and this path is straight as well as curved. Okay, and this is the model, experimental model of the mobile robot. So it is similar to the model that I've shown before. So the kinematics of this particular robot is similar to the one given in these slides. So some specifications. So the wheelbase B is 0.33 meters and L is 0.3 meters. The wheel radius is 0.06 meters and the linear forward velocity is 0.2 meters per second. So this is the, you can say, the maximum velocity, forward velocity that we want to drive at. So basically on straight paths, it should drive at around this particular velocity, 0.2 meters per second. And the angular velocity limit, omega max, is 1 radians per second. So this is the maximum angular velocity that it can have. So alpha is chosen as 0.85. So please note that alpha was the parameter selecting which of the two errors, lateral or the heading error, has more importance. So in this case, you can say that since alpha is 0.85, lateral error has more importance than heading error. So this parameter was obtained experimentally. But this can also be optimized using an optimization algorithm. So it is difficult to optimize if you are testing on a particular hardware platform. If you don't have a software model of the exact software model of this hardware platform, then it's difficult to test on the hardware, because on the hardware, optimization algorithms can apply different choice of parameters, and they can make the hardware unstable. So that is one of the problems when trying to optimize directly on the hardware. If you obtain a software model for this robot, then it is easy. You can just do a simulation and choose those parameters using simulation in the simulation. And then some details, more details about the control system. So it was running using a ARM Cortex M3 microcontroller or LPC1768 microcontroller, and had a modular actuator system. So these DC motors with gear head, encoder, sensor, and controller. So the controller, so this is the low level controller, had a closed loop PI controller at 56 kilohertz, right? So this is a low level controller. So this controls the individual wheel motor speeds. So individual wheel motor speeds are controlled by this controller. So basically what we provide to the low level controller is the steering that we want or desire. So desired steering and the desired velocity, which is the 4 linear velocity that we want. And it basically adjusts the wheel speeds to achieve those steering and velocity. So next, some details about vision system is given here. So basically it says a low cost USB camera is used with MATLAB's image acquisition toolbox. 640 by 480 images are acquired at a rate of 7 Hz. So the vision system was really slow because of the limitations of USB camera. So if you have a different type of camera, then maybe it would be faster. And the size of the images of the line ahead is 640 by 480, which is the width and the height. And then this model is used, and the parameters of this model are computed, which is a pinhole camera model, to obtain various parameters. So basically over here, what we are trying to do is we are trying to map from an image, we are trying to determine the exact location on the floor of the elements in the image. For example, if the image captures the line and the curvature of the line, then we want to find out where exactly on the floor the lines are. So that is why we have to model the vision system as well. So that's what we have done here. And then our modeling revealed some parameters such as the 3x3 camera matrix K. So which was found to be this, using MATLAB. So we have used image camera calibration toolbox in MATLAB when to obtain a camera matrix K as this. And the extrinsic parameters of the camera are found to be this. So this is R and T. So these are the radial and the, sorry, these are the rotation and the translation values of the rotation and the translation matrix. So basically this matrix convert the points on an image into points on the floor. So it says radial and tangential length distortion was taken into account to compute these parameters. It says images of the path projected from image pixel coordinates to ground plane. So these basically parameters project the image pixels into coordinates on the ground plane. So XY coordinates or XYZ coordinates on the ground plane. So we'll see an example of this, which is here. So you can see an image that was captured by the vision system of the robot. So this is a 640 by 480 image. And you can see in this image, you can clearly see the ground. So this camera is mounted on the mobile robot. You can clearly see the ground, and on the ground, you can see the lane. Okay. So the lane is marked in this way. And you can see it's fairly straight, but then when we approach this part, there is a bend here, which bends into that direction. So this is an original image taken by the camera system of the mobile robot. Now, using those parameters or the model that we did before for the vision system, converts the model into XY locations. So basically, this orange this trapezoidal orange area that you see, so this is XY coordinates. So this is the XY plane of the mobile robot. So this trapezoidal orange area that you see are the area on the floor that is marked by the corners of this image. And then this part, the dots here, or the square dots, basically are dots on this particular white line. So these are dots, and as you can see, the dots are linearly taken on this particular image, but then over here you can see how they vary. And then this blue line is basically like a model. So this is model of this the shape of the white path on the ground. So basically this is like a polynomial model of this particular line on the ground using these points. So using this model, we can estimate the curvature. We can estimate the curvature of this particular bend. So that is the whole idea. So we have calibrated the vision system so that any point on the ground is projected to a XY plane. So basically in the XY plane, this is the area on the ground that is captured in this camera. So this particular area, which is given by these orange lines. And the points on the line are extracted from this image. And then when they are projected here, they appear as this. And then we find a model for these points. So we do the model using polynomial modeling. And then we find the curvature of this particular bend. So the curvature here, this part is basically straight. But then when we approach this part, this is like a curved path. So we want to compute the curvature so that we can provide this information to our control system. So that is the whole idea here. So next, some experimental results. So the result of the design of the control system for the straight path tracking, you can see that the lateral and the heading error. So initially, you can see that in the second figure here, you can see the actual path and the robot position. So initially the robot is positioned at some offset from the actual path, which you can see here. So there is no heading error initially. But then the lateral error is initially large. It's almost 0.1 here, or slightly more than 0.1. And then when the for 12 seconds. So when the mobile robot starts moving, the controllers basically try to reduce the lateral error. So initially when it's trying to reduce the lateral error, you can see it turns this way, and then tries to track this path. So the heading error increases initially, and then basically when it closes in on the lateral error and it goes over the path, then the heading error goes almost to 0. So that is what these two graphs are showing. So the next is the actual paths tracked by the mobile robot of 3 different curvatures. So one is 3.3 meter inverse, which is the blue line, 2 meter inverse, which is the red line, and 1.43 meter inverse, which is the green line. So this shows the actual position or the trajectory that was followed by the mobile robot in tracking these three different curvatures. So basically, the one with the blue line has the narrowest curvature, and the green line has the least narrowest, or it has a wide curvature. So the mobile robot was able to follow all 3 different trajectories or 3 different curvatures. And then on this particular graph, you can see the velocity, the 4 linear velocity when tracking the curvature, which is the blue curvature here. So you can see, since blue line has a very narrow curvature, so it is like a tight band. It is a very narrow curvature. So initially, so the 4 linear velocity is 2. That's our target velocity, but the fuzzy system, can you see it reduces when it approaches the curved path? It reduces the velocity, slows it down, and then the velocity increases when it is able to turn, and then it again detects a straight path here. So as it goes here, velocity is high. When it comes here, curve, velocity drops, and then when it goes here, velocity increases again to 0.2 meters per second. So next, we can see the same thing for the other 2 curvatures. So medium curvature, which is 2 meter inverse, we can see that initially it has 0.2 velocity, and it tracks that. When it comes to the curved path, the velocity decreases slowly, and then when it is able to turn and detect a straight path, the velocity increases back to 0.2 meters per second. And for the wide band, which is not very tight, so it is a very wide band. So normally when we drive over the wide band, some of us, we don't even reduce the speed. We just keep driving at 80. So in this case, the mobile robot, when it detects a wide band, it does reduce speed slightly. So you can see the differences in the speeds for the 3 tracked paths. So the one which has a very wide band, the speed reduces, but not by a lot. Okay, so it reduces slightly, not by a lot. But the one which has a very tight band, the speed reduces way down. So that is what these graphs are depicting. So which shows that our fuzzy system is working for the fuzzy velocity controller, and the steering angle controller is working. So in conclusion, what we have concluded from this work is that fuzzy logic-based method to control mobile robot path tracking is a good method. It's an unconventional method, and we are able to control a real-time mobile robot using this method. So the real-time mobile robot is able to track a path So we had some limitations in the vision system, whereby our vision system was slow, but then again, the unconventional fuzzy logic-based controller is able to track paths of different shapes, or sorry, different cavities on the ground. So we have a fuzzy steering controller and a fuzzy velocity controller. Steering controller controls the steering angle of the mobile robot when it comes across caved paths, and velocity controller controls the forward velocity for safe path tracking. And we say safe path tracking here because thing is, if a mobile robot is used on in a fulfillment center whereby we want to deliver packages, we don't want it to go very fast around corners, because what will happen is if it goes very fast, then it might drop some of the packages that are loaded on top of it. So that is the idea. We don't want to do that. So we want to do safe path tracking, as well as it is safe for whatever application it is used for, that is package handling or part handling. Okay. So the path information, like the lateral and the heading errors, are given by the vision system. So which we said was, so there were some limitations. So some of the limitations was low pixel density, or you can say the size of the image. Okay. Because if you increase the size, our processing becomes very slow. So we had to work with a 640 by 480 image. And the other limitation was low. So it was working at a rate of 7 Hz. So if you have a faster camera, then this rate will increase, or faster capture system, then this rate will increase, and the performance of the controller will also increase. So we did experiments on the actual hardware platform, not on the simulation. So we did experiments on the actual robot hardware platform, whereby we obtained parameters experimentally. Using different parameters, and we noted which parameters provided good performance. And then experiments on straight and caved path shows the effectiveness of the proposed approach. So we did experiments on the straight and the caved path, and we recorded the trajectory, and we recorded also the velocity of the mobile robot. And we were able to show that our targeted or desired trajectory was being followed, and our desired velocity was also obtained. So we decided that on caved paths to slow the mobile robot down, and this is what we saw through the experimental results. Next is a video demonstration of this particular concept, and I want to show it here. So let me switch to the video, and then I can demonstrate. So this is the video. So you can see that the mobile robot was tracking a straight path. Now it's over the caved portion, and you can see that it has slowed down, and then it picks up speed. Now it's again approaching a caved path, so it slows down. So currently this cave is is a wide cave, so it doesn't slow down much. But when it comes to the narrow caves, you can see it really slows down. And then on the straight path, speeds up. On the narrow cave, slows down even more. And then speeds up on the straight path. On the wide cave, it slows down, but not by a lot. And then on the straight path, it goes fast. So it is able to do trekking of the path, and it is able to slow down on very tight bends. So that is what we see through this video. So again, we have come to the end of this slide. So this was the final example in this topic, fuzzy systems, so fuzzy controls. So you have seen through this example how fuzzy logic can be used to control a mobile robot to track a specified path on the floor. So I hope through this example, you are able to basically understand what fuzzy logic is or fuzzy controls is. And basically this topic, fuzzy controls, is still an active area of research, and I want to leave it open for you so that you can pursue, if you are interested, you can pursue research in this area later on after completing this course. So also, this is the final lecture, and I want to thank you all for joining in this course, and I hope, I wish you all the best in your exams. And I would like to say also, I want to mention that the topic of fuzzy controls will not be covered in the exams. So this is like an open topic for you, or to inspire you to venture into intelligent controls, such as fuzzy logic-based control systems, and to allow you or to foster lifelong learning. So basically you have to, if you are interested, you can take up this topic and do more research in it, and you can come up with your proposal for your next program, of course. So in case if you are interested in doing further studies, you can do some research in this area and then come up with your proposal, and you can further improve this area as well. So it's totally entirely up to you. So that's where I would like to leave you. So this basically concludes our course, and again, I hope you would submit all your assignments on time, and then there will be an online final exam in this course, the details of which I'll provide you through emails or through messages on Moodle. So thank you once again, and all the best.